All right, so today I'm trying something new, which is that I'm recording, I mean, I've sort of written everything that I want to talk about today except the theorem. Because I think, like a theorem, like when you follow a proof, it should go slowly. Because if a proof goes fast, then it just like slips out of your head. But maybe with the definitions, especially the ones that we're revisiting, they could go a bit quicker. So we're going to try, and hopefully it's not too fast. We will see. So this also gives me an opportunity to make it a bit prettier than it normally comes out when I'm doing it on the fly. Okay, so last time we introduced three tree properties, one called the tree property, one called the tree property of the first kind, and one called the tree property of the second kind. So let's make it look like this. So hopefully that's still legible. So the tree property is the same thing as saying that you have KTP for some K. So to say that a formula has the tree property means there is a K, and there is some collection of tuples, A eta, indexed by omega to the less than omega, such that two things happen. So the first thing is that paths are consistent, which means that if you take a path through the tree, an element of omega to the omega, and you look at all of its finite initial segments, and you plug the associated parameters into your formula, so you get like a empty set, and then like a0, and then a00, and then a000. If you look at that collection of formulas, that's a consistent partial type. However, if you fix a particular node and you look at its immediate descendants, that should be a k inconsistent collection of formulas. So we had an example of this where we talked about, what was it, the dense linear order, and you can look at nested intervals. So at the first level, I just take any pair of rational numbers, and I look at the formula that says I'm between them. Okay, and then you can look at the next level. You take that interval and you break it up into infinitely many subintervals, and then the formula says I'm in this one, or I'm in this one, or I'm in this one. Those are all pairwise and consistent, but it's consistent to be in both the big interval and any one of these subintervals. Then you divide each one of those subintervals into infinitely many subintervals. That gives you the next level in the tree, and so on. So that builds a tree which witnesses the tree property, 2TP in fact, but it has a stronger property, which is this one in the bottom left, which is the tree property of the first kind. So that also says that paths are consistent, just like before. But now you'll see that in the definition of the tree property, I was agnostic about the question. If I take two things that are incomparable, but not descendants of a common node, is it the case that they are consistent or not? So in the tree property of the first kind, I've made a decision. I say that they are all inconsistent. And this happens whenever you have the strict order property, which I said was an exercise that you could do last time. Okay, and then there's the other extreme, which is you take the definition of the tree property and you make everything that isn't forced to be inconsistent consistent. And it's more convenient in this case because you lose track of the tree relations to index it by an array. So you have an omega by omega array of tuples a, I, j, as I and j range over the natural numbers, and you have some k such that the analog of paths being consistent is that somehow a choice of one element out of each row gives you something consistent. So the way I formalize that is I say, if I take a function and I imagine this function is picking something out of each row, then plugging the choice from the first row and the choice from the second row and the choice from the third row and so forth into the formula gives me a consistent partial type. That's written in the first thing. Phi x ai f of I, as I ranges over the natural numbers, is consistent. But if I fix a particular row, and then I move my formula just along instances of that row, that should be k inconsistent. Okay. So the rows you should think of is like what happens when you look at the children of a common node in the tree property. And then you should think about these functions as moving along a path. But because you've insisted that things are inconsistent, even when they're just incomparable, but not children of a common node, you no longer have the tree structure. Okay, so these are the somehow two extremes. And if we get time, I'll give an example where you have the tree property of the second kind, but not the tree property of the first kind. But I want to get to the theorem first, so we'll do that. All right, then we talked about tree indiscernibles. So there are two kinds of tree indiscernibles that I want to talk about today. One we mentioned last time, which is these STR indiscernibles, and then there's another version that we'll need today, also called S indiscernibles. So we have two languages which are appropriate for studying trees. There's a third one, which we'll mention later, but for now we'll just use these two. So STR, which stands for strong, although strongly indiscernible trees mean something else, so it's very frustrating. So we'll just stick to the name STR indiscernible. So here we have three order relations in the language. One is the tree partial order, which is this like triangle with a line under it. The next is the lexicographic order. And then the third is the length partial order. And then we have the meet function, which you need. Then LS, S here stands for Shelah, these aren't my names. You have the tree partial order, the lexicographic order. You no longer have the length order. You have the meet function. And now you have unary predicates, Pn, as in ranges over the natural numbers. And these are naturally interpreted as identifying the nodes at level n. So I described the interpretations below. I say omega to the less than omega may be viewed as either an LSTR or an LS structure in a natural way. So what are the interpretations? Well, what are the elements of omega to the less than omega? They're sequences of finite length whose whose entries consist of natural numbers. So eta is extended by nu. If whenever I restrict nu to the domain of eta, to the length of eta, I get eta. So that's just extension of sequences. Eta meet nu is the maximal initial segment common to both eta and nu. And because we're working with finite trees, this always exists. Finite length. I mean, it's an infinite tree, but finite length nodes. That always exists. If you look at the lexicographic order, what does that mean? Well, eta is lexicographically less than nu. You think about it just like a dictionary. Eta either is extended by nu, or they're incomparable. And if I look at their meet, to get to eta, I go in the I direction. To get to nu, I go in the j direction, and I is less than j. So after their common initial segment, I look and see where they go next. So, atavistic comes before atomic in the dictionary because they have a common initial segment of at, but then to get atavistic, I concatenate with an A, and then to get atomic, I concatenate with a 0. Okay, it's like that. It's like the dictionary. I think you all know this, so I'm just saying it so that you have time to write it down. Okay, and then the length thing, it's a partial order, and it just suggests that, it's not a partial order. I guess it's a pre-order, right? It's a pre-order on the elements. So the relation holds. Eta is less than in length nu, just in case the length of eta is less than the length of nu. And the reason this is not a partial order, it's a pre-order is what I should say, is because, of course, two things can be at the same length without being equal. So you have an equivalence relation of saying, neither eta is less than in length to nu, and nu is not less than in length to eta, i.e. they have the same length. That's an equivalence relation that identifies the levels. So notice that you have a relation which says I am in the same level in the STR language. That you have this equivalence relation which identifies the levels because you can define it actually in a quantifier-free way using this length comparison. The classes in this pre-order are exactly the elements of the same length. That's an important point because there are lots of things where we'll need to preserve what happens at things of the same levels. Okay, and then lastly, I just say that you interpret Pn to hold of a node eta just in case eta has length n. Okay, so it should be clear from the definition that if you start with something which is STR indiscernible, then it's also S indiscernible. Because, for example, you can expand any, you can essentially, like, you have this notion of two. goodness. Okay. Shelby's upset that there's a dog on the street. Okay, so STR indiscernibility strengthens S indiscernibility, but the converse is not true. You can be S indiscernible without being STR indiscernible. And the example I want to give here is this picture. So in S indiscernible trees, tuples indexed by nodes at different levels need not have the same type. Why? Well, because what is the definition of indiscernibility say? It says when two things have the same quantifier free type, the things that they index should have the same type, right? Now, if things are at different levels in the S language, you know that like if one is at level 6, then part of its quantifier free type says P6 holds of me. And if something is at level 8, then its quantifier free type will say P8 holds of me. So the quantifier free types of things at different levels are different. So the definition of indiscernibility doesn't say that they have to have the same type. Whereas in the STR language, something at level 6 has the same quantifier free type. I mean, a single node at level 6 is the same quantifier free type as something at level 8. And so paths in the STR language are actually indiscernible sequences, but in the S language they're not, and that's a big difference between the two. Okay, so an important fact that we will use is that S indiscernible trees and STR indiscernible trees have the modeling property, so we can find indiscernibles based on them, so locally based on them. Now, we mentioned that in the STR case, this follows from a theorem in combinatorics called the Halpern-Laukli theorem, which says that finite trees, like the age of omega to less than omega, considered as an STR structure, is a Ramsey class. So that follows. Now, in the case of S indiscernible trees, you can't really just use the theorem. You can't use Linz-Gauss theorem immediately because it's not a finite language, and we needed that it was a finite language. I mean, at least we used that. But what you can do is you can sort of prove it for finitely many levels, and then observe that the age is going to be like an increasing union, or do it by compactness if you like, for any of the finite levels. And for finite levels, you can actually just do it by hand using Ramsey's theorem. I mean, you can prove that indiscernible sequences exist by first looking at the top level, and then looking at the next level, and then looking at the next level, sort of inductively. So it's a nice exercise to prove that I-indexed indiscernibles have the modeling property when I is omega to less than omega, understood as an LS structure. And like I said, I mean, normally we say I-indexed indiscernibles. Here I'm going to talk about S indiscernible trees or STR indiscernible trees. And what that just means is I'm thinking about omega to less than omega indexed trees, where I'm thinking of omega to less than omega either as an LS structure or as an LSTR structure. And that'll be clear, some context. Okay, now one thing I wanted to do next was I wanted to fix this confusion that happened last time. I mean, I think the confusion was mostly mine about what elongation means. So I wrote down a definition which is much clearer, I hope, of elongation, and then a picture which also is clearer. So here is the idea. So take your favorite K, fix it. Then given an element of omega to less than omega of length n, I'm going to define a new element of omega to less than omega of length n times k. Okay, so I'm going to multiply the length by k. How do I do that? Well, if I'm given eta, then the new element that I define will be called eta tilde. And my rule is that I'm going to somehow spread out the entries of eta every k steps. So if I plug in j to eta tilde, if the element that I'm plugging in is a multiple of k, then I divide it by k and I plug it into eta, and that's going to be the output. So I wrote it here. Eta of eta of j will be equal to eta tilde of j will be equal to eta I if j is equal to k times I. So if I have a multiple of k, I divide by k and then I plug it into eta and then I take the output. On the other hand, if I have something which is not a multiple of k, then I just output 0. So I just pad the non-multiples of k with zeros. And then that gives me something of longer length, where I've somehow spread out all of the non-multiples of k entries with zeros. So I'm padding. right? With zeros, spreading everything out by k. This is the elongation. So, well, okay, it's not the elongation exactly. This just defines an operation, and then the k-fold elongation of a tree, a eta, eta in omega is less than omega, is now a collection of k tuples from the tree, where I look at a eta tilde, a eta tilde concatenated with 0, all the way up to a eta tilde concatenated with 0 to the k minus 1. So now my tuples have grown by k. I'm replacing each tuple with a k tuple of those tuples. And they're going to be indexed by these sort of padded bits. So let's look at this picture. So I drew a picture of the threefold elongation of a tree. So, okay, if I start with the empty node, what is its length? It's 0. So so 0 tilde should be the empty node as well. So what is the threefold elongation of the tree going to give me at level 0? I get a 3 tuple where I have a sub empty node, a sub 0, and then a sub 0 2. That's written at the bottom here. So it's like here, right? And then at level 3, I'm allowed to branch. And I can add like a 0 or a 1 or a 2. And let's look at this thing here. So B2 here is a 3 tuple. What does it start with? Well, I have a 0 2 concatenated with 2. And then the next thing is a 0 2 concatenated with 2 concatenated with 0. And then a 0 2 concatenated with 2 concatenated with 0 squared. That's a 3 tuple like that. So I've taken this 3 tuple, and that's the next thing. That corresponds to B2. Now, suppose I want to look at B2 1. Well, I just take a sub 0 squared 2, a sub 0 squared, and then I add a 1, and then I add a 0, and then I add 2 zeros. And that gives me a 3 tuple like that. So this is some elongation. Is the procedure clear? Okay, so what's the point? The point is this gives me a way of constructing new indiscernible trees from old. So the fact that we have here is that if you start with an S indiscernible tree or an STR indiscernible tree, and you replace each node with this elongated tuple, that stays S indiscernible or STR indiscernible. And okay, how do you check this? Well, take two in tuples from omega to less than omega, eta bar and nu bar. You want to check that B eta bar has the same quantifier free type as B nu bar. But you know what those come from? Those come from certain so if eta bar and nu bar were in tuples, then now they come from certain n times k tuples from omega to less than omega, indexing elements of the original tree. So you have to check that those n times k tuples have the same quantifier free type if the n tuples did. And that's grungy. That's a really gross kind of check to do by cases, but you can do it. I mean, there's nothing complicated about it. You have to be careful to make sure it's true. But once you know it's true, it's very easy to believe that it's clear, right? That like all of the tree relations that you see, things like length, lexicographic order, extension, are all preserved by this passage from eta to eta bar, and so the indiscernibility is preserved. So I leave it to you to check. It's not particularly enlightening to do, but it's character building maybe. So I don't know. It's worth trying. But for now, feel free to just believe it because it's true. All right. And then before we get to the theorem, I want to talk about one other kind of indiscernible structure. So the first one is called a mutually indiscernible array. Okay, so what is a mutually indiscernible array? So you have an array of tuples indexed by pairs of natural numbers. You have aij, and we think about this as like a big matrix, right? And the rows we'll write like a bar I. So a bar I is like the ith row. So I look at the sequence aij as j varies. So yeah, so I'm I'm letting j vary and I'm fixing I. So I'm drawing that as a row here. Now, the rule for being a mutually indiscernible array is that if you look at that sequence a bar I, it should be indiscernible over all of the other rows. So in this picture, I have selected some row, let's call it a bar I. And what I'm asking is that that sequence is an indiscernible sequence over everything that's highlighted in blue, over all of the other rows. Okay, so somehow if you freeze everything and then you start moving along this row, you're indiscernible. Okay, now if you additionally can move vertically indiscernibly, then you're a strongly indiscernible array. And what does that mean? It means you can look at the sequence of sequences, the a bar i's, and as you vary I, that should be an indiscernible sequence as well. Okay, now strongly indiscernible arrays appear under different names in the literature. So these were introduced by Artyom in his thesis. And at the time, they were called very indiscernible arrays. And then people made fun of him and he changed it. So I think you can still find a whole bunch of papers where these are called very indiscernible arrays. And I don't know, if you go to like Logic Dinner at some future time, you should make fun of Artyom for this and he'll get embarrassed. All right, so that's like the prerequisites. And now we're going to move on to proving the theorem. So are there any questions about anything that we've done so far?
I have a quick question about the definition of a strongly indiscernible array.
Yeah.
So, I mean, maybe I'm just missing something obvious, but each AI bar is an infinite tuple, so to speak.
Yeah.
So what exactly do we mean when we say that that's an indiscernible sequence?
Well, one way of saying it is that if I take, well, it's exactly the same notion. So you know what the type of an infinite sequence is, right? You just, I mean, if you have an infinite sequence whose variables, let's say its variables are, or it's indexed by the natural numbers. So you take variables xi indexed by the natural numbers, and then you can look at the formulas that hold, you know, of finitely many of those where you choose certain subset of the variables, right? So it's the same thing as saying that if I restrict it to any finite subtuple, that's indiscernible. I mean, but you know, because formulas are finite things, so to have the same type means that, you know, if I restrict to any finite piece and I look at the formulas that are true for that finite piece, I can't distinguish. So if I take finitely many rows and then I take some other finitely many rows also in the same order, and I look at the type of that intuple and I look at the type of this intuple, then I expect those to be the same.
Okay,
that make sense?
Thank you.
Cool. Yeah, I should have said, by the way, that this a strongly indiscernible AI, there was a missing piece, is a mutually indiscernible array. So it's like a mutually indiscernible array plus the rows should be indiscernible. Sorry, was there another question?
Nick, can you hear me?
You're quite quiet. Let me turn you up. Try again.
Yeah, I'm saying so. Just the same question as Alex. So the formulas in the type are like different formulas contain different number of variables, right?
Yeah.
You will have a formula of 3 variables and a formula of 100 variables and so on, right?
Yeah. So you look at all formulas in all possible variables, and the idea, I mean, another way of seeing it is like, suppose that I just, I mean, so it's equivalent to saying if I restrict to a finite subtuple, and I look at like the corresponding subtuple in each one. Oops, it should correspond. So I look at the corresponding subtuple of each one, right? Like, let's assume each one of these is indexed by the natural numbers. So suppose I look at the subtuple indexed by 6, 9, and 13. So in each one, I look at 6, 9, 13, 6, 9, 13, and I look at that indiscernible, I look at that sequence of triples. I want that to be indiscernible. And saying that the sequence of infinite tuples is indiscernible is the same thing as saying that all of its finite subtuples are indiscernible sequences when I look at the corresponding tuples in all of the things. Yeah, but I mean, as long as you know what the type of an infinite sequence means, and you know it's something in infinitely many variables, then you know what indiscernible sequence means. Yeah. All right. Good. Okay, so now let's prove the theorem. So let's recall what the theorem is. So I like to call this Shelah's second dichotomy theorem. Because this theorem doesn't have a name, and it's nice to give it one. But who knows if that name will stick? I think if you say it, no one will know what you're talking about. But it's good to have things with names. So this is what I'm going to call it. All right. So what's the theorem say? It says suppose T is not simple, then T has either TP1 or TP2. Now let's recall what it means for T to have one of these properties. For T to have one of these properties means that some formula does, modulo T. Okay, so what does it mean for T to be not simple? It means that some formula has the tree property. So this says that if some formula has the tree property, then some formula has the tree property of the first kind, or some formula has the tree property of the second kind. And as we'll see, the theorem can be strengthened a bit. What you could say is that if a formula has the tree property, then either that formula has the tree property of the second kind, or some conjunction of instances has the tree property of the first kind. And that's a bit closer to what we proved about SOP and IP, if you recall. So what we proved is that if you have a formula with the order property, then either that formula has the independence property, or some conjunction of positive and negative instances of the formula has the strict order property. So it's close, but okay, it's not so important to know exactly what the formula is for us. So we won't worry about optimizing. We're just going to get the theorem right. So let's start with the lemma, which is going to be important for getting the indiscernibility right. And in fact, this lemma was missing. So this theorem was first proved by Shelah, and then it was reproved in different places where people were trying to give expositions. And they actually always made mistakes with indiscernibility. This is why I sort of wanted to do this class in a kind of slow way, because people make mistakes in almost every paper in which tree indiscernibles appear, because it's just easy to miss some subtle thing. So this lemma was missing, and it was later noticed by Kim and Scow. So I'll attribute it. So the theorem is due to Shelah sort of morally, although I think the first complete correct proof was given by Kim Scow only a few years ago. So what this says is, suppose A eta in, or let me say it this way. So suppose phi witnesses KTP with respect to some S indiscernible tree A eta in omega to the less than omega, then if phi is in TP2, so the formula doesn't have TP2, there is some n such that if nu I less than n, is a sequence in omega to the less than omega with two things happening. So the first is that the length of nu I equals the length of nu j for I not equal to j. And nu I meet nu j is equal to nu I prime meet nu j prime for I not equal to j, I prime not equal to j prime. then phi, so I should say pairwise distinct, just to be pedantic. They should be pairwise distinct. Then phi a nu I less than n, is inconsistent. All right, so this is a kind of technical looking thing, but I'll draw a picture and then it'll be clear what I mean. Okay, so the statement is very long, so I guess I don't want to take it away before you write it down. But what am I saying? I'm saying that like if I take a family of nodes, which are all at the same length, so they're all at the same level, and they all have a common meet. So they're like, so maybe like those of you that have thought about set theory have thought about like the delta system lemma, right? What is a delta system? It's like a collection of sets such that any two of them have the same intersection. This is like the analog of a delta system for a tree. Any two of them have the same meet. So you have a bunch of things which all have the same meet pairwise, and they all have the same length. Then there's some bound which tells you that these have to be inconsistent. Okay, so let's prove it. So, so as T is, or let's say as phi is in TP2, so by compactness, there is some n.
What is NTP2? So is we define TP2, but
Oh, NTP2 is not TP2. Sorry. So yeah, this is the model theory convention. So n plus property always equals not property. Yeah, this is super frustrating that like in model theory, normally we define everything in terms of the bad property and then we take its negation. So, you know, like what are the nice theories? The nice theories are the ones without the order property. What are the nice theories? The ones without the tree property, the ones without IP, like in IP, in TP2, in TP1, in SOP1. I mean, we have all these n's around. You'd think that we should just define our properties positively, and then because that's what we focus on, but instead there are always all these negations. And so you end up with people, you know, talking about particular structures, and they're always saying like, oh, this is not NIP, which seems like excessive. I mean, we're all classical logicians here. We believe in double negation elimination, but it's still not efficient linguistically, I suppose. Yeah, so NTP2 means it doesn't have TP2. So because it doesn't have TP2, there is some n by compactness such that if A, I, J, now I'm going to write I less than n, J less than omega is a mutually indiscernible array. Okay, now before you protest, I know that when we defined mutually indiscernible array, the index set was omega and omega. So we had omega many rows and each one had width omega. But you can perfectly imagine how to modify the definition when the height is n. When you have n rows and still width omega columns. What do? You just have n sequences, and whenever you fix one of those sequences, it should be indiscernible over the others. So it's still a mutually indiscernible array. It just has finite height now. What do you get? Phi x a I 0, I less than n, is inconsistent. Okay, let's think about why. So let's draw a picture here. So here we've got our mutually indiscernible array. So mutually indiscernible. Now, suppose I know that this is consistent. All right, so the zeros column is consistent. I look at AI0 as I ranges over the numbers less than n. Then what do I know about this sequence? Well, that's also consistent, right? Like the bottom sequence is indiscernible of everything else. So first off, I know that this is consistent because I can move this thing to here. And that's indiscernible over everything else. Then I know that I can move this thing to here. So what does that give me? That gives me that this thing is consistent. Then I can move this thing to here. So that gives me that this thing is consistent. And then I can move this thing to here. And that gives me that this thing is consistent. So using indiscernibility at each level, I actually know that if the zero column is consistent, then every column is consistent. So suppose now that there's no uniform finite bound on how high I can this approximation. Sorry, so sorry. Sorry, no, this is really bad. When, what I said is correct, but let me add a statement. When a bar I, let me get rid of this. Okay, when phi x ai j, j less than omega, is k inconsistent for all I. So, okay, if I knew that all of my rows were k inconsistent, but I had no uniform finite bound on the height, then by compactness, I would be able to build an infinite array with the property that all the rows were k inconsistent and all of the ways of snaking through the array were consistent. And what is that? That's TP2. Does everyone see that? So if I can find an array of height n where the rows are k inconsistent, so you know these rows here are k inconsistent, and the zero column is consistent, then that means that all of the ways of snaking through are consistent. And then by compactness, I can find via the arbitrary large approximations an infinite one, and that gives me TP2. That's exactly what TP2 says. Does that make sense?
So n here might depend on k?
Yes, n depends on k. So fix k. So given k, so this k was fixed here. This you know, you're exactly right that like the compactness argument that I would run, I have to fix the k, and then let n vary. So the n I get from compactness will depend on k, 100%. Okay, so now let's find our n. Let n prime be the max of n here that we got, and then k. So k was given. This is the inconsistency that we have in the definition of the tree property, and then now we get this capital N, which tells us how high we can build an approximation to the tree property of the second kind. So now consider pairwise distinct nu I less than n prime with length nu I is equal to length nu I prime, and all pairs or all distinct pairs having a common meet, as in the statement. Okay, So case 1 is the length of nu I equals the length of nu I concatenated with, or sorry, meet nu I prime for some I not equal to I prime plus 1. So you extend the meet by 1. Okay, so the picture here is you've got the common meet, which we'll call eta. So this is like nu I concatenated with nu I prime, I not equal to I prime. And then all of these things are children of this common node. So then these things are k inconsistent. Hence, in prime inconsistent, just by definition of the tree property. So if they are descendants of a common node, then the definition of KTP just tells me already that they're k inconsistent. So any k of them is inconsistent, and therefore any k of any in prime of them is inconsistent, because in prime is the max of n and k. Does that make sense? So now we have to worry about the other case, which is that you're farther away. So case 2 is that the length of nu I is strictly greater than the length of nu I wedge nu I prime plus 1 for I not equal to I prime. Okay, so then what do you look like? So I'm going to do this sort of quickly. You have eta, which is like the common meet. So this is nu I meet nu I prime. Then you extend something. And you have like nu 0, nu 1, nu 2, all the way up to nu n prime. Okay, so we took our collection like this. All right, now choose xi and ni such that nu I is equal to xi concatenated with ni for all I less than n prime. Okay, and we'll notice that the xi's are pairwise distinct. Because we're not in case 1. So if the pairwise, if the xi's were common, then they would have a common initial segment, and then they would differ only by 1. So because we're not in case 1, I can find something that they extend, which are all pairwise distinct. So we're going to call that xi. So this is like xi0, this is like xi1, this is xi2, this is xi n prime. All right, so this is where we're at. Then the thing to observe is that if I look at the following thing, so I'm going to define Aij is equal to A sub xi concatenated with j. So let's look back at our picture here. So I look at all of the infinitely many successors of these things. So now I'm looking at an array where the elements are like this. So the crazy thing, which is kind of very cool, is that we know that Aij, I less than n prime, j less than omega, is mutually indiscernible. by the S indiscernibility of the tree. Okay, so this is really the key point. So let me zoom out. So if we look at this tree here, it follows from S indiscernibility of the tree that if I fix one of these sequences and I start moving around inside, I don't change any of the quantifier free types that those things have with respect to the other sequences, right? Because what do you know? I mean, you know that as you move between these blobs that I've circled, you don't change the length. You don't change the placement in the lexicographic order with respect to the other sequences. You don't change your placement in the tree containment, the tree partial order. So the quantifier free type is preserved. And that means that these are a mutually indiscernible array. Also, you know that phi x a I j, as you vary j, is k inconsistent. Why? Well, let's go back to the picture. What are these blobs? These are descendants of a common node. We've reduced back to case one, right? Where you look at descendants of a common node, children of a common node, and these were assumed to be k inconsistent. So now, if phi x a nu I for I less than n prime is consistent, then by mutual indiscernibility, you have phi x a I 0 as I less than n is consistent, contradicting the choice of n. So what was n? N was the first place where we can find no mutually indiscernible array such that the 0 column is consistent and then the rows are k inconsistent. So here, let's go back to our picture. I mean, the picture proves everything, right? So if we knew that this was consistent and this was consistent together, so I don't know, let's make it green, I guess. So if we knew that this was consistent, then in fact, any choice, one from each one of these blobs would be consistent by mutual indiscernibility. And if that's true, then what did we find? We found, you can think about this as like the first row, and this is the second row, and this is the third row, and this is the fourth row, in a mutually indiscernible array where the rows are k inconsistent. And then that gives you an approximation to TP2 that you assume didn't exist. And so that's a contradiction, and that gives you the lemma. So, okay, like always, I was convinced that we would finish the theorem today, and we're very evidently not going to. But I think we will finish it. I mean, okay, we will finish it next time. Even if we don't, we will. And then we will move on to forking and dividing and simple theories. So we'll do less sort of with the combinatorics of trees for a little while, although that will definitely come back. And we'll focus on independence relations for a brief moment. All right, are there any questions about the way this argument went?
Could you just scroll down briefly to the
Yeah, to which part?
at the end?
Oh, okay. Right, so this part here says that rows are k inconsistent because from the definition, these corresponded to descendants of a common node. I mean, these were a sub ci concatenated with j. So if the things we picked were consistent, then the 0 column is consistent, and so everything is consistent. And that's the contradiction. All right, any other questions? Nope. All right, so I'll stop sharing then.